Okay, next session is about methods for solar potential in built environments. The next speaker is Martin Thibault. Martin is a senior researcher since 2021 in can you just say the naming?
It's TNRS.
Okay, yeah. TNRS. Yeah. Okay. He works in the laboratory focusing on physical modeling and the harvesting of urban solar resources from component scale to the territory scale. You say that you are also singer, so you prefer this microphone, right?
Singer, yes. I have a two singers.
Singer.
Yeah. Yeah.
The applause is yours.
I'm not a good singer, but I like so don't give me a microphone in the evening. Yeah. Okay. Does this work now? Okay. Yeah. Okay. Okay, so thank you, Gabriele, for inviting me to present here. Today I will talk about one of the work we are conducting on large-scale multi-criteria sorting of the roof for PV suitability. Very quickly, I come from working at the CNRS, the French National Center of Scientific Research. It's based all over France, and I'm based here in the National Institute of Solar Energy in the Alps, so I'm kind of used to this type of weather, but for the last 2 years we have no snow anymore, so it's kind of pleasant to see snow here. This is more or less the idea of what I am and we are doing, working on physical phenomenon at the city scale, more on the distribution of irradiance and spatial temporal availability of it. We scale up to add some societal and economical aspects into multi-criteria for PV deployments, and we try to reach the scale of the territory to be doing decision aiding for the local decision makers. So today I will present a study that we are doing, and it started in the framework of the J2 Solar project, an integrated project led by Gilles Lestieux here in IEA SHC, and also we participated at the University Savoie. A very quick context here. So in 2023, I think we are close to 1 terawatt peak installed all around the world. And a question that I have, and that we had a very nice introduction to it, is quickly, to your knowledge, what would be the installed capacity in 2030 or 2050? So what are the projections? So I remind you that here in 2023 we are at 1 terawatt hour. And so if you look at the projections, then these are the projections. It's not from me, it's a work from Professor Trutnevitz at the University of Geneva, but they reviewed all the projections around the world, and we just see that, okay, here we are, and based on all the scenarios from the IPCC, from the IEA, from research institution, then these are the different scenarios. So it goes from nothing to 70 to times 70 of the capacity. So it's very difficult to know where we're going to be, nobody knows. But what we know is that it will be massive, and also a lot, it will be urban also. So this is what we are trying to assess, is how we can make this change massive in a short amount of time. So what we were doing in this project is that we were working on a big territory of 2,000 square meters and trying to find, okay, how can we allow this deployment quickly? So first of all, we try to see, okay, what are all the decisional criteria that are put into the balance when we want to assess if a roof is suitable for PV panels or not. So we started to do the list because the project was more at the beginning on the energy side, let's say, calculating the irradiance on the roofs. But we quickly realized that this information about the irradiance on the roof is almost not used in the decision making when you want to install a PV panel. You look at other indicators, other factors, but saying to someone, okay, you have 1,200 kilowatt hour per square meter per year on the roof means nothing to most of the people. So we try to make a list. Here it's we have some factor, it's non-exhaustive, it also depends on the country you are in and many factors, but here are some of the criteria that we found in the literature and within the experts we talk with. Criteria about energy, of course, we are talking about PV energy, but also criteria about the grid connection. Since you inject PV in the local grid, you need a grid connection, you need it to be designed to absorb the power flow that you are going to sell to the grid. So this is very important. There are more and more concern about environmental criteria, which is good. So how do you quantify it? You can quantify the CO2 emissions, the energy payback time, the recycling capacity. You have here we had a very good example of problems you can have with technical or structural integrity of the roof, because with PV panel you add load on the roof, so it can induce problem depending on the integration and the initial structure. Economic, of course, this is usually what talks best to investors. But how do you assess it? Is it payback time? Is it the levelized cost of energy? There are many questions behind it. It's not difficult to answer. Heritage and social, it's very important, especially in Europe, for example, where you have a lot of heritage building that you want to preserve. And last but not least, very difficult, I'm not an expert at all, but juridical. I know that in France there are many projects that cannot go until the end because, for example, the insurance company won't insure the building because you change the roof. So everything could be ready and insurance can say no, stop. So if we want this change to be massive, we would like to find a way to have a reliable information on these criteria, and also at very large scale, because if you assess one building after the other, it will take 50 years to complete this goal. So we want a very large scale information tools. Here you see that it's very multidisciplinary, so we have to work on multidisciplinary approach. And at the end, we want to design a decision aiding tools to help actors. So what we try to do here is to provide a very simple sorting that would aggregate as much as possible of this information and just provide a grading, A, B, C, D, on the roof and its suitability to be equipped with PV panels. So here you have another view of the workflow that we designed. I haven't mentioned it, but we work on the Greater Geneva in Switzerland and France. Here it's more it's not Geneva. Here it's the Île de la Cité in Paris. But yeah, so this is it. So unfortunately we are not able to evaluate all the criteria because we wanted information at a wide scale, so 300,000 buildings, and some of the information you have, some you don't have. So we have, let's say, just partial information in this study, which are highlighted in red here, but we can have this information for each buildings we are interested in. Then, when you are doing with a multi-criteria approach, you want to know, okay, how do I aggregate these results and for whom? Because depending on the actors, one would prefer to have to put a high priority on economic, other one on heritage. So you have to take that into account when you try to aggregate these results. Here we used something called ELECT method. I won't explain it, but it's a very nice method for multi-criteria approach, which allows to take into account the human process of decision making. Because sometimes, for example, if you want to buy a car, if there is a 10 euro difference between two cars, that won't make one car better than the other. So you have this kind of thresholds, which are indifference threshold, preference threshold that you can take into account in the decision making. And this is a method that allows to take that into account. And then you have we provided a simple classification, and we try to validate it on existing PV systems. Before showing you the results, I won't explain all the criteria we evaluated, but just some of them. So we calculated the self-sufficiency potentials for all the buildings in the Greater Geneva. So we had the solar potential on the roof of this building, and we also managed to calculate the electric consumption of each building in the Greater Geneva. And then here we can calculate this area, which corresponds to the self-consumed energy. If we look at here the distribution of the buildings in terms of its statistical distribution, sorry, the payback period here, it's not a good one, but yeah, we had kind of different way of self-consumption, because depending on the area, you didn't have the same policies in terms of subsidies, and we didn't have also the same quality of information, and whereas we had some difference in the distribution. Another one that you know well is the reduction in CO2. So here we compare the CO2 emissions of the PV panel to the CO2 emissions of the European Union, which we had to do because if we were using the CO2 emission of Switzerland or Norway, or not of Norway, but of Switzerland, then adding PV panels wouldn't make CO2 benefits. So we have to use the European mix, which makes sense because electricity has no borders. So, and in Norway, yeah, but you have an even more interesting case since you are almost the lowest in Europe in terms of emission per kilowatt hour produced. Yeah, okay. For the economic, we had many discussions. We didn't know if we wanted to use the LCOU, the levelized cost of energy, or the payback period. For example, the payback period is relevant if you are talking to a citizen because you understand it very well. In 10 years, you are fine with your money. Levelized cost of energy is more maybe at a higher level for decision maker, urbanists, or governments that wants to know how this investment will compete with other energy production. So each of them have an interesting case. Last one here is a heritage. So you have a lot of very protected and very interesting heritage area in the Greater Geneva. For example, here we represent you all the protected area. So depending on the color or on the how it's presented here, it's different type of protections, different rules behind them. So we couldn't it's difficult because it's a big text, so you cannot put easily a mark on it like this is good protection or bad protection. It's very specific, but we discussed with the experts in the field, and we still managed to define, let's say, high level of protection, which means that it would be almost impossible to equip this building with PV systems, and medium protection in which it's possible if you do some additional work on integration or discussion with local experts. So here you have an idea of the entire area covered. You recognize here the Lac Léman and the city center of Geneva. And so red is very good ranking, and yellow is, let's say, to be confirmed. So additional work would be needed to see if this building is suitable or not. Basically, a lot of power, according to what we have done, a lot of the power is, like Mr. Third, is within A-ranked buildings, so very suitable buildings, which is kind of good here. Just here, since we work at a very big scale, we have 210 municipalities. Then you can see difference in behavior. So here, this is an area where you have only C and B buildings, so no suitable because it's protected in terms of heritage. And here you have a kind of a recent municipality with good irradiation. So this is the type of municipality you should prioritize. So just to finish, with this type of analysis, we can provide kind of decision help for the decision maker. So we would advise them to start with the A buildings, and you can reach you can have much better results than the goal that they set for 2030. And then if you have to, you should peek into the B building and avoid the C buildings. Yes, so that's it. If you want more information, I'm here to discuss, and here are some references in case you want to have a look at it. Thank you.
Thanks a lot, Nathan. We'll go ahead with the program. Then the question will come later for you, for sure. Our next speaker is Martina Giario. She is a research fellow at the University of Padua, Italy, and she's a building engineer and architect. Her research focus is on analysis of topics related to environmental microclimate aspects and optimization of solar potential inside the urban context. The floor is yours, Martina, please. Welcome.
Thank you so much, Gabriele, for the opportunity. So, with the research group at the ICEA department at the University of Padua in Italy, with Professor Rossana Papparella as a responsible, we are working on the topic of solar potential analysis, try to evaluate the portability of this data to an urban scale, defining a methodology that could combine the data obtained from the solar potential simulation and the territorial data managed in a GIS environment. To reach this goal with the research group that also participates at the Task63 work, the process has been developed following 3 different steps applied on a specific case study in order to have a complete overview of the situation and also to assume consequent intervention. And specifically, the 3 different stages consist in the urban microclimatic analysis, the solar potential analysis, and the development of design hypotheses. This was necessary in order to have a complete overview also of the intervention that can be implemented to try to solve some problematic issues identified, allowing the improvement of the energy response within the existing building context, including thermal and human comfort and sustainability. And the 3 different phases required themselves internal implementation with the use of different softwares and tools. And in our specific case study, the following software were used. And now each stage of the process will be shown in more detail. In fact, it was chosen a case study in which to test and develop all this methodology. And Padua is located in the northeast part of Italy, in the Veneto region. And due to the global warming and climate changes conditions, temperatures are changing and the climate map are being altered, bringing local conditions and temperatures near to the Mediterranean climate, characterized by very hot summers and not too cold winters. The area belongs to the University of Padua, and it covers a very large surface of about 50,000 square meters. Here there are mainly buildings used as student classrooms, offices, laboratories, and also the university canteen with all the outdoor spaces. And after a detailed phase of surveying of the current conditions of buildings and urban surfaces, some large-scale microclimatic analysis were carried on to try to show the influence of the pavement materials in the effects in the surface and air temperatures and the perceived human comfort as well. For this analysis, it was also essential to have information and data about all the extension of the green areas, including the exact location of trees, for example, and with all their main characteristics. Through simulations carried out with the software MVMet, it was possible to show the influence of specifically the payments in generating the phenomenon of the urban net island, allowing the visualization in peaks of surface and air temperatures reached especially during the hottest hours of summer days. And especially this process made it possible to begin a redesign phase of the entire area, where the redesign of the replacement, especially of the existing payments, was assumed with the use of cool payments specifically. And these changes can already bring a lot of benefits across the area, decreasing the surface and air temperatures and increasing the perceived human thermal comfort. The next step was to extend the analysis to the field of large-scale solar potential study. And based on a 3D model, it was possible to obtain information about the solar potential of building and surfaces using, for example, tools for grasshoppers such as honeybee and ladybug. However, the question posed in this case are many, and the ones we have tried to answer are in particular two. And this is the first one. Can data calculated on a simplified model be compared with a real situation? We developed a methodology that could take into account the data obtained through simulation in a simplified model, modifying it according to some corrective coefficients to make the data as close as possible to reality. This results because each building have particular characteristics given, for example, by the presence of windows, balconies, or particular exterior overhangs, shadings, and canopies that are not taken into account in a simplified solar potential simulation. They could influence, for example, the area available for the installation of the new photovoltaic system, but also the efficiency. This particular condition, as I said before, could not be taken into account in a very simplified model that can be obtained from a territorial database and generated through script using, for example, the Urbano tool. Through this tool, it was possible to obtain a very simplified model starting from an OSM file. And the information used for the generation of the model are mainly the building heights, the functions, and the number of levels. And to avoid these issues relative to the extreme simplification of the data obtained, the proposed strategy is to find corrective coefficients that, when multiplied to a simplified input, can return a result as close to the calculated solar potential, for example, in a detailed model. Okay. These coefficients are directly related to the rate of glazed and unglazed areas, for example, and to the possible shedding due by large overhangs. And the process of calculation of these indices derived from visual and geometric surveys, and to evaluate the property of the surfaces and also the available areas. But this process presents some limitation because it isn't a very fast and immediate process. But once these values were identified and implemented in the simplified solar potential calculation, the accuracy of the data was verified and validated by generating the same simulation with a very detailed model of the same buildings. And the second question, on the other hand, is about making this data functional in an urban scale. And specifically, the question is if can this data obtained in the simulation environment be functional and implementable at the urban scale? Once the solar potential was calculated, the focus was to transpose the data for each individual building, grouping them by affiliation and exporting all the information. With the creation of code in Grasshopper, the whole process ended with the overwriting of the starting OSM file, as it was enriched with all the new information simulated of the solar potential of each individual building. And overwriting that file makes the information exportable to any data processing software, such as QGIS. And the value of this process is that it allows the creation of a sort of solar cadastre in which all the data for each individual building are grouped together in a single database. And the subsequent and last step involves the development of an energy upgrading project from the urban surfaces to the redevelopment and redesigning of the building envelopes in the area. Considering only one of the building inside the area, after a detailed energy diagnosis performed with the Edit Klima software, it results that its energy performance class is very low. However, thanks to all the analysis and simulations carried out in the previous phases, it was possible to redesign some regenerative interventions, such as the introduction of an external envelope, the replacement of the existing windows and doors, and the installation of custom-made photovoltaic modules on the roofs and facades. All these changes introduced in the building bring to the achievement of energy class A4, which is significantly higher than the static condition. And by analyzing the results in a quantitative way, all the values presented for the estimation of the solar potential are calculated in a cautionary way over a time range of 1 year. It is also important to highlight that the application of the new photovoltaic systems only on the roofs and the facades of the buildings is not the only application possibility. In fact, there are an increasing number of innovative methodologies that integrate photovoltaic systems into various elements of urban design and less usual elements of buildings for a greater efficiency. And the development of this methodology aims to provide different approaches for the evaluation of the solar potential data simulated. And in the context described, the future development of the work can certainly concern and be directed toward the identification of the interference between mitigation systems and the applied PV panels, and secondly, the implementation of photogrammetry to accelerate the surface detection phase, and finally, the comparison between the energy production and energy consumption to evaluate the self-sustainability of the buildings. And the work has been developed up to this stage, and the results of the analysis are still in the process of the final testing and elaboration. Thank you.
Thank you, Martina. Third presentation for this session is that by Xavier Azan.
Yes.
She's a PhD in Toronto Metropolitan University. Give me a second. The research, your research explores solar envelope, solar neighborhoods with the use of machine learning. Yeah. I really thank you to come here from far away.
Thank you so much.
Thanks a lot. And the floor is yours.
Thank you.
take that?
You can take whatever you yeah, this one. You want this microphone or the other one?
This one's okay.
Okay.
Hi, everyone. My name is Tiberia, and my PhD research looks at the application of machine learning to the design of solar-centric neighborhoods. So I'm looking at it from the Toronto perspective. My supervisor is Dr. Miliana Horvath. Okay, so just for some perspective, the access to the sun is very important from the standpoint of neighborhood energy resilience and sustainability. We all know that there's a growing traction towards identifying issues concerning long-term livability and resilience of neighborhoods, especially because the solar exposure is linked to passive solar heating inside buildings. And we all know that daylighting is a very important human physiological need. So why is this important? And basically, the problem that is dictating my research is the current phenomenon of increasing densification in Toronto nowadays. There's an unprecedented level of densification with tall buildings cropping up everywhere, and they're closely clustered together. And what that results in is basically the overshadowing of neighborhood buildings and surfaces, specifically rooftops and facades, that could be potentially used for integration of active solar technologies, be it photovoltaics or solar thermal technologies. And this actually conflicts with Toronto's 2050 net zero energy goals. Toronto has this objective of attaining net zero energy status in all the buildings, either through retrofits, through implementation of on-site solar technologies. So this is very important from that standpoint. There are existing guidelines that concern solar access in Toronto, but they specify only solar access to sidewalks for a certain duration during the year, but they don't concern solar access to neighborhood building surfaces. So this is where my research comes into play. So this brings to the need for adopting architectural forms that can allow solar access on neighborhood buildings and surfaces. Dowles introduced the concept of solar envelope back in the early 1970s. And basically that is defined as a construct of space and time, the physical boundaries of surrounding properties, and their period of assured solar access. So as you can see on the image on the right side, that dark gray surface is the maximum volume that you can develop on that parcel of land, so that the solar rights of neighborhood buildings are respected. And basically the neighborhood is a nice place to live in. So just to throw some context here of different scenarios that are existing in Toronto. So you have the existing neighborhood. I have simulated the level of shadows that exist there on the March equinox, which is basically from 8 a.m. to 4 p.m. And in the existing scenario with the current configuration of buildings, we don't see so much of overshadowing except near the north side there. Not the north side, that's the west side, yeah. And then now the current scenario where you've got a lot of high-rise development. So you've got that tall building there, which is dark gray in color. And during the March equinox, this tall building is casting significant shadows. Imagine what repercussions that has on, if you were a building owner of buildings around and you have photovoltaics there, basically your photovoltaics are no longer feasible to be there. Then the new scenario is what my research looks at is, what if we were to attain a certain level of density that is okay, that is acceptable, but then also develop a building form that can allow solar access to neighborhood buildings. So say if that was a residential building right opposite the building in the green, you would still have some daylighting entering in, which is important from a human physiological perspective as well. So this kind of architectural form, solar envelopes, is very applicable to many of the main avenues in Toronto, especially those that run from the east-west direction. And these buildings around these avenues are mid-rise buildings. So instead of developers building tall buildings, it is appropriate to build buildings that are in harmony with the existing context. There's growing traction towards adoption of solar envelope buildings in Canada. So as we can see here, that is the Vancouver House, and it was designed, the architect was Bjarke Ingels Group. And basically, it's one of the reasons why it's such designed in such a way is because it allows for solar access on a park that is nearby. So also important from a social construct as well. So my PhD research aims to address what is the maximum solar envelope development density that can be achieved in specific Toronto neighborhoods, while also ensuring a minimum level of solar access. So we need to have that balance between density. Of course, we need to house people and also ensure that neighborhoods are sustainable. What is the position of buildings relative to the development side, where if we were to ensure solar access, it would compromise the extent of solar envelope density? So to answer those questions, I'm using a mix of simulations and data analytics. So the solar envelope simulations can be done through a computational platform known as Rhinoceros, which I'm sure a lot of you are aware of, using Grasshopper and Ladybug, because they are features within that tool that help perform such simulations. And then data extraction and analysis. So basically data that is representing those neighborhoods is extracted, and it's extracted in a form that can be later processed in Python, and where I train and test machine learning algorithms. So basically the simulations that I'm looking at are looking at the neighborhood morphology and the solar envelope form. So there needs to be a way to be able to represent the texture of the neighborhood that I'm looking at. So there are two categories of parameters that I'm looking at. First is the spatial category, and the second is a temporal category. Spatial is basically neighborhood morphology that governs the solar access to the rooftops and facades, which I'm interested in. And going deeper into the roof and the facade categories, we have subcategories that relate to the characteristics of that surface. So say, what is the position of that roof relative to the development site? What is the slope, orientation, height, and area? And a similar characteristic is applied to the facade. The solar envelope building that will result out of the simulations can be represented in terms of its volume, its density, its floor space area. So that is basically the outcome metric that will later be used to train the machine learning algorithm. And temporal parameters, of course, the level of solar access is varying across the year depending on where you are, what season you are. So solar access period, and then solar access duration, so how many hours you're looking at. So in order to process such a large and diverse data set, there had to be a tool that could help me achieve a meaningful understanding on the relationship between the different parameters. So machine learning comes into play here. It helps me determine what parameters are important in respect to their influence on the solar envelope form. It helps me data process with a lot of ease. And since I'm looking at a lot of randomized configurations of neighborhoods to generate these solar envelope forms, there's also that degree of randomization potential in determining different outcomes. And another concept is the architectonic parametrization, how changes in the neighborhood form can actually affect the volume and form changes in the solar envelope building. And then, of course, machine learning algorithms help in predictive analytics. So the machine learning algorithm that I'm looking at, and from an extensive literature review on this subject, is random forest. Random forest has been applied in a lot of urban level studies where it has been used in the prediction of geometrical characteristics, specifically the height of buildings. It has a very good performance just because of the way it works, and especially in terms of prediction analytics. It demonstrates a good level of stability because of low prevalence of error. So this is an example of data collection from the simulations. We have certain fixed parameters, and certain variable parameters. So variable parameters govern the characteristics of the roof types here, and then further geometrical characteristics are varying in that. So the data collection template, which will later be used for the algorithm training and testing, can be categorized as site dimensions of the parcel of land where you're developing the solar envelope building level parameters, or the spatial parameters that I've discussed earlier, again, differentiated in terms of the roof and facade characteristics, the climate information, and then the outcome metric that we're trying to predict out of all of this training testing process. So a simple animation here shows how just varying neighborhood texture, neighborhood characteristics, building heights can affect the level of solar envelope form that we're looking at. Currently, we have 2,000 plus data points, but we're looking to increase that to create a very large and diverse data set that can help improve the model. Randomizing the building height, random surface selection, because we understand not all buildings need to be having that solar exposure. So getting that kind of mix in play, and then machine learning training and testing is underway. So this is just a snapshot of some of the simulations that has already been carried out. And as of now, initial training and testing is producing a great result. So we have an accuracy of 85.92%, but we want to increase that to 90%. We are getting some influence of urban morphological features in the model performance as well. So this is a great sign that it's working. So as we can see in this research, random forest is good at predicting parameters that are influential in the solar envelope density metric. Model accuracy is 85%, but this will be increasing, hopefully with more diverse and large data set. And this will help in decision making in regards to solar envelope building development in existing neighborhoods, so we can have livable cities in the future. Thank you.
So, no, it was perfect on time as well. Okay, I got a message that if you use this microphone, you need to be very close to your mouth.
Okay.
You are Italian,
So
it's better if you use this one, because
No,
we move the microphone every. Use this one.
Yeah, I will move the other.
Okay.
Yeah.
But be careful, okay?
Yes.
Yeah. I need to present you.
Yeah,
Next speaker is Mattia Manni. He is a postdoc at our Department of Civil and Environmental Engineering. He worked as a freelancer on urban planner for the enhancement of suburb area around Perugia train stations. Yeah. And since 2022 is author of publications in the field of energy, green energy, sustainable development, solar analysis, smart cities, and other topics. So Mattia, please be careful with the microphone.
Yeah.
The floor is yours.
Okay, so I will just move this end and not so much. I'm Mattia Manni, I'm a postdoc at NTNU, and I'm going to guide you to this project and introduce you to the first activities. So before I start with the presentation, I would like you to focus on these stripes, because these stripes are the reason why we are here today talking about solar radiation in a Nordic city like Trondheim. Why solar energy in Nordic environment? We have been discussing that a lot today. Someone might reasonably think that there is too little sunlight here, that is too cold, or is not cost effective to invest in solar energy sector, but those are false myths. And the reason is on these stripes. As you can see, the stripes color are defined accordingly to the average yearly radiation across Europe from south to north. And the black lines are highlighting the latitude of Rome, Prague, Berlin, Copenhagen, Oslo, Helsinki, and Stockholm. Except from Rome, that is actually Mediterranean Europe. You can see there are not much differences between continental and Scandinavian area. So if it's reasonable to invest in Germany, it should be the same in Norway as well. Fortunately, Norwegians are starting being aware of their solar energy potential and the solar energy potential of their lands. So as you can see from the graph, the installed capacity for solar power in Norway has been increasing tenfold between 2015 and 2020, and there are not data on this graph for 2021 and 22, but I mean the reaction is almost the same. So the trend is that. And there are new opportunities to exploit this solar energy potential. It's not just building integrated PV, which is already a good advancement, but it's also agrivoltaic system, we have seen with Steve before, and offshore photovoltaic plants. Norway has knowledge for building, for working offshore. They have already worked offshore with oil station and fish farms, and those technology background can help a lot also in the solar sector. So what is missing now? What is still missing is a tool that supports stakeholders in their planning efforts. And here it comes IEA, here it comes the fund of IEA. And yeah, the aim of the project is to develop a solar cadastre, which is a 3-dimensional solar maps, which is more advanced than the one that are currently used because of the level of detail of the geometry, but also of the analysis. And the Helios project is arranged around 7 work packages. Everyone is an important stone to pave the way toward the solar cadastre. So every work package is focusing on a specific aspect like monitoring, implementation of pilots, modeling and simulation, stakeholders involvement, and solar forecasting. The 3 pillars that we have identified so far in the implementation of this solar cadastre are solar data sources, geometry detection techniques, and solar irradiance model chain. Pillar 1, solar data sources, we have been investigating different data sources ranging from numerical reanalysis, satellite observation, and ground monitoring network. The ground monitoring network we are using now is the one at Glossagen that also Steve has shown before, and it comprises all the facilities where solar sensors are installed on, and the facility equipped with a PV system. So we can both monitor the solar irradiation at the surfaces, but also the power, the energy generation from the PVs in case they are equipped with. And yeah, the main activities within Pillar 1 has been a comparative study on solar data sources. So we have been implementing a simulation workflow, and we reiterate that with different data. So the data we were using as input were different variables, solar radiation variables, and they were differing because of the variable, of course, and of the time resolution. So the first simulation was run with global horizontal irradiation from IRA5 land reanalysis, which is hourly dataset time series. The second one was using direct and diffuse irradiation with 1 minute time resolution from satellite observation. And then we have measured values as input. In that case, is the diffuse and direct irradiation from Glossagen with 1 minute time resolution. And in the last case is global tilted irradiation measured on the same panel, plane of the panel, still from NTNU's InterSolarNet. Because sometimes, as we have been told today, numerical modeling cannot predict properly what is the final result, like here. And it's not just matter of model, it might be matter of data source. And yeah, here in the scatter plot, you can see the modeled energy output against the observed energy output, while on the right, there is a heat map for 2021 and 2022, where is reported the difference between the model and the observed values. You can see that the red and blue colors are like under or overestimation, while green is a good agreement. And the data source that permitted to estimate the PV production in a better way was the one using global tilted irradiance measured on the plane of the panel. And yeah, that was, and in general, I mean, measured quantities, measured data set are better than numerical analysis or, I mean, satellite observation. So should be prioritized the monitoring in local. And pillar 2, yeah, is geometry detection techniques. I have to admit, I'm not the expert in this pillar, so Professor Lon Chauhan is responsible for this part. I will just show you in brief the activities, and if you have questions, we will forward to him, and maybe we will provide you the email or his contact. So yeah, what we've been doing so far in this pillar has been more related to the detection of the elements of the facade and implementation of semi-automatic techniques to reconstruct the building geometry. You can see here this deep learning-based method to detect window, wall, balcony, door, roof, or shop at the first ground, at the ground level from street view images. And those information are, of course, of primary importance to reconstruct the layout and then to build the 3D model. Then, that is what the solar cadastre of EDIS is aiming at. So we are ambitious and we want to have a high level of detail, in particular a level of detail 3, which is the one usually recommended to run solar analysis, energy analysis, and of course solar analysis. And pillar 3, solar irradiance model chain. Model chain, for those who are not aware of what is literally a chain of models. So it's a combination of models to perform multiple tasks. When it comes to solar irradiance model chain, there are 2 main stages, which are decomposition and transposition. The first stage permits to split global horizontal irradiance into diffuse and direct contribution, and then we transpose this to the tilted plane with transposition models. So this solar irradiance model chain has to be flexible, which means that we can delete one of the stage. If we have direct and diffuse information, we don't need to go for global horizontal, but we need that to be bidirectional so that we can decide the way we want to follow. More in detail, those are how the composition model works. So they split the global into direct and diffuse, but then transposition are a bit more complicated because diffuse radiation is not coming homogeneously from the sky. So we have diffuse isotropic, but then there are some parts where diffuse irradiation is concentrated, like circumsolar zone around the sunrise or around on the horizon. And those quantities needs to be into account to simulate that properly. The main activities within pillar 3 have been a validation study of 4 decomposition models at high latitudes. So we have been using measured global horizontal irradiation to fit the model and then estimate the direct and diffuse fraction. These values, the results have been then compared with measured quantities for October 2021 and August 2022. The 4 models were 2 quasi-universal models and 2 quasi-local models. A quasi-universal model means that is a model that is trained with global dataset. A local model uses local datasets to be trained for the training. In this case, the 2 local models were trained with data from Bergen, the first, and the second with data from high latitudes weather station. So it was not just Norway. And yeah, the results here you can see this cluster plot, that the gray dots were the measured values and the red one were the modeled one. So, and they report the clearness index against the default fraction. So it's the model that demonstrated to perform the best was the Young-Fair model, which is one of the quasi-universal model. And so despite the other one where the local model were trained with local data, the quasi-universal one was working actually better. So what's next? Regarding pillar 1, we are now moving to the exploration of the future. So we are going to investigate how climate change scenarios are affecting the estimation, the analysis, the solar analysis. And we are, regarding pillar 2, we are now focusing more on the optical property of the surface. So we want to implement a semi-automated or fully automated detection techniques for optical properties of the surfaces, and which permit us to simulate reflection within the urban environment. Pillar 3, now we should focus on the second stage of the model chain and shift the focus on the transposition modeling. So what you should remind from today is, again, these stripes, that there is solar energy potential in Norway, and that there are many opportunities for optimal exploitation of that. And then, of course, there will be soon, hopefully, a tool to support you in designing solar strategies. So that was all from my side.
Thanks a lot, Mattia. So now I invite all the speakers of this session just to sit here in the middle. Can you help me, please? In the meantime, I ask if there is any question from the audience here or online. Please say your names and your affiliation.
Hello, so my name is Harry. I'm a master's student at NTNU. I had one question for Javeria. It was a super interesting presentation, so thank you. I guess I had a question about how you juggle maybe the output of the model that gives you kind of like ideal parameters for a building with what might be a more feasible building to build, or like the ease of construction. I guess I'm wondering, in my head, I'm thinking, okay, you have a model that gives you the best parameters for like access to daylight or access to, you know, radiation. But I'm thinking potentially maybe those parameters might give you like an irregular building shape that might be difficult to build. And so I'm wondering if there's anything in the model that maybe gives weight to something that's not only efficient in terms of sunlight access, but also maybe ease of construction as well.
Thank you for your question. So basically, the model has parameters that reflect the solar access to different surfaces. So what I'm trying to determine is how, depending on what surface you will assure solar access to. Thank you. So depending on what surface or surfaces you want to assure solar access to, what is the maximum level of density for that new development that can be achieved. So the parameters are more geometrical expressions of the neighborhood surfaces, be it rooftop or facade, and how wearing solar access to different surfaces would result in different solar envelope densities. So it's not so much about the energy aspect or the day lighting aspect. It's about how urban texture needs to be accounted for when we're designing for new development. I hope that answers your question.
Can I ask one? Yes. I just had another question
Yeah.
for Martina. That's cool. So I'm just selfishly interested in your use of NVMet because I'm also using it for a project and I find it quite difficult. I was wondering, I know you mentioned some simplifications that you had to make for your model in NVMet, and I was wondering just generally like what sort of simplifications were necessary for your NVMet implementation, and just if you had any general issues with that.
Thank you for your question. And yes, I need to simplify a lot my model because I have, for example, balconies or canopies that I cannot take into account in my simulation, and or for example also the windows. Because I use different materials for windows and the not glazed surfaces, but I take care because if you take too much glazed surface, it's a problem when you write in the simulation environment because they cannot simulate very well the surfaces. So this is a limitation of the software. Yes.
Any other questions or comments from the audience?
Yeah.
Robert?
Yes, so Robert from Skanska. First, I have a question to you, Mattia, because when I work with Sun, in the early stages I use a program called PV Solar. Not PV, yeah. Pivot. Yeah. No, PV Sol Premium. And in that program, there's a huge amount of, you can choose many different type of climate files, meteor norm, PVGs, and also you can choose different models for diffuse shading and all those things. And it's very difficult for me to know which one to trust the most. So in general, I have a huge distrust in the numbers I get from the simulations. Your tool, will it help me to make a better or to help me choose the most correct model for my simulations?
Yeah, so I didn't get the question, sorry.
I mean, when I use the software,
Yeah.
the software has many options for use of models.
Which one are the best?
Yeah.
It depends on the option, but I mean, for the diffuse model that you was mentioning, I think is like what we did, what I was showing you before. There are different contributions, and some models, like the fastest one and the simplest, they usually consider just the isotropic diffuse, which is just hemisphere diffuse radiation, and they don't consider like horizon brightening or just circumsolar radiation. So I think it depends on the different model alternatives, and now I don't know which are the alternatives provided by the software, but I assume that, I mean, most of the software usually provide like different transposition models. So, I mean, the user usually are allowed of selecting that. And yeah, it depends. You should check which are the model and the literature. And actually there are some limitations, like for instance, there are some transposition models that have been demonstrated not to work perfectly with vertical surfaces when transposing to vertical surfaces. So it depends really on what you want to model, which is your case study, and how fast you want to perform the simulation, and that's always affecting, I mean, the accuracy of the result. But I think the point is that you are never relying on sure or certain results. So I think it's important to show that there is some inaccuracy and estimate that and say, okay, we estimate this. We are, I mean, in science working like that, but might be the same consulting. I mean, you can just say, okay, we simulate that and the accuracy is that one. So is this value plus minus 5%, or I mean some inaccuracy values, and that permits to be on the safe side.
Yeah, exactly. Yeah. And then just another quick question to Martin. If I understood your presentations, you know how you now have all these A buildings, right? Which are the most suitable for PV production. But who is going to use the information that you are now presenting?
Yeah, that's an excellent question. I'm not sure it's available yet. And one thing which I didn't explain is that you have to use who you want to give this information to. So if you want to give it to municipality, you won't have the same weights as for a citizen or for private investors. So for now, we have something we based on, I think, on as if a single citizens wanted to use it, but to make it operational, we would need to know who would be interested in it, and if it's, for example, the municipality, then would maybe redesign the weights. But also another thing is that the solar cadasters in general are not tools for, I mean, yet they are not tools for on which you base the final decision. Usually it gives you a first ID, and then you redo something, you redo a study, because architects or installers will always tell you, oh, there is something you missed, because you work with such big data that you always miss something. So it's more a communication tool, I would say, to try to go quickly and to give awareness on it. So it could have both this activity. So maybe doing a first design and decision aiding ground, and then adapt it to the kind of users.
Thanks. Any other questions from the audience?
I have one from
From you?
I can move there.
Okay.
Okay, no, it's about, because you say that you try different level of details when analyzing simulating solar irradiance, and you noticed that there was a difference within the model. So I wanted to know if you have, like, if you monitored somehow with some pirometer, like the radiation, and check. I mean, we assume that the most detailed model is the best one, but we don't know. Maybe the other one, that is the one giving the. So I want to know if you have validate or check with
Yes,
some measures.
because we use also some sensor applied on the buildings, so we can check the results, and we find a difference of 30%, about 30% between the detailed one and the simplified model. The difference between the two models, but the detailed one was the results was closer to the sensor results.
Thanks.
Okay, so if there are no other questions, we are perfectly on time. So we just now close the session. Thanks, Martin, Mattia, Martina, and Jahinda. And we are ready for lunch. So lunch lasts, I think, 40 minutes, something like that. So we come back at 45 minutes past 12. Thank you for the speakers and the audience. So we see each other later. In the meantime, the survey is there. If you want help us with the subtask B, please do that during the lunch break. Thank you.
Yeah, was that again? But for the equipment, fine, yeah. guys, and if you consider the work, they on the. I think that's